Hello, everyone, and thank you for joining today's webinar learning event hosted by Owens Corning on the topic of chilled water insulation systems. My name is Alec Cusick, and I am a technical services engineer for Owens Corning's technical insulation business. Before we begin, I'd like to review a few housekeeping items. First, at the bottom of your screen are multiple tools that you can use. All the engagement tools are resizable and movable, so you're welcome to move them around as you like. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the event, you can submit them through the Q&A engagement tool. We will try to answer these at the end of the event, but if a fuller answer is needed or if we run out of time, we will be following up via email. Please ensure you have a stable internet connection during the event. If your slides fall behind at any point, pushing F5 on your keyboard will refresh the page. You can find additional answers to common technical issues in the Help tool at the bottom of your screen. And a recording of this event will be available after the event concludes and can be accessed using the same audience link sent to you earlier. And without further ado, let's move into our main topic today, which will be around design considerations for insulating chilled water systems. Before we get started, I'd just like to set the agenda for what we'll be talking about here today. We'll start off discussing a little bit about Owens Corning for those that may not be familiar with us. Then we'll move on into common challenges faced with chilled water lines within commercial spaces. We'll then discuss some design considerations you may want to consider when designing your own insulation system on said chilled water lines. Then we'll introduce cellular glass insulation as a potential insulation material for use on these systems. And finally, we'll wrap things up at the end discussing some technical service offerings that we as a company can offer. Owens Corning is a global industrial and building materials leader with 3 integrated businesses dedicated to the manufacture and advancement of insulation, roofing, and fiberglass composite materials. We have over 19,000 employees that operate across 33 different countries around the globe, and we're very proud to have been a member of the Fortune 500 company list for 68 consecutive years. Owens Corning offers a wide portfolio of insulation products that can be utilized in many different areas within modern commercial buildings. Our product portfolio includes both open and closed cell insulation solutions, including FOAMGLAS Cellular Glass, fiberglass, Paroc and thermofiber mineral wool, and FOAMULAR extruded polystyrene. With that being said, we'll go ahead and move right into our main topic for today, which will be around chilled water systems within commercial buildings. Specifically, we'll start off discussing some common challenges that one may face when designing insulation systems around them. Today's commercial buildings are complex facilities, which could include airports, hotels, schools, offices, and so on. Each of these facilities brings with it many challenging components and obstacles to design around. Chilled water lines within the HVAC commercial cooling systems are no exception, and the insulation systems that are installed on them are a common area where reinstallation after initial construction may be required due to unanticipated system failure. Now, when we talk about chilled water lines, there's commonly going to be a temperature range that we're referring to. This could be down towards 36 degrees Fahrenheit for a chilled water supply line, all the way up to 55 degrees Fahrenheit for a chilled water return line. Now, if you ever had a cold beverage sitting on a patio on a hot summer's day, you're already familiar with the phenomenon we're going to be talking about, and that is condensation and moisture buildup all along that cold pipe surface. This condensation can bring about a variety of challenges for the insulation system that happens to be installed on that cold pipe. We're going to be talking today about strong vapor drive into and onto that cold pipe surface underneath the insulation. And that will bring about an emphasis on the performance of the insulation system's vapor barrier. If that vapor barrier were to become compromised, the system would be subject to failure and could bring about a variety of issues. These issues could become immediately apparent, or in some cases, they may remain hidden for months or even years, waiting to be discovered down the road. Here we can see some of the most common examples of those issues typically found on failed chilled water insulation systems. They could include dripping water, causing slip and other safety hazards, the formation of mold and mildew, which could be a problem for indoor air quality within the building, or the corrosion of the metal pipe or other nearby equipment, as well as increased operating costs due to the loss of insulation efficiency. Starting off with our first example, in many cases, the most immediately noticeable symptom of a failed insulation system on a chilled water line may in fact be the presence of dripping water from the system itself. If water vapor is allowed to penetrate the vapor barrier of the insulation and condense on the cold piping surface, it can build up to the point where it then re-escapes the insulation and drips down below to whatever happens to be underneath. If that's a floor, then it poses a slipping hazard for any nearby personnel. If that's a ceiling tile, it can cause unpleasant staining. And if there's equipment nearby, then that water could drip onto it and cause corrosion concerns for whatever the water happens to come into contact with. Another potential consequence of a failed insulation system on chilled water lines involves the formation of mold and mildew. Mold and mildew can grow in the presence of both a food source along with moisture. I will mention that most insulation materials don't inherently provide a food source for mold to grow off of. However, most of the time the food source is introduced to the system after the fact. That could be something as simple as dust debris, nearby floating skin cells, or other byproducts of the natural environment. Once moisture is introduced to the system at that point, then you're at risk for the formation of mold and mildew to grow, posing an immediate indoor air quality concern for those around. Mold has been linked to many symptoms such as chronic fatigue, headaches, asthma attacks, and other lung illnesses, and toxic mold is the focus of a growing number of legal cases across the country. Because of all this, the design considerations that may lead to the formation of mold in commercial buildings is becoming a topic under much more scrutiny in recent years. Another byproduct of introducing moisture underneath your insulation system involves the potential for corrosion under insulation, or CUI, to occur. Some key ingredients for the corrosion of carbon steel include the presence of oxygen as well as liquid moisture. Oxygen is almost always readily available, whether it be from the air or dissolved in water itself. So once condensation takes place and liquid moisture becomes readily available, you do become at risk for corrosion to begin occurring. Corrosion can damage the outside of piping over the span of multiple years and can remain hidden by its very nature and out of sight until it's well too late. In the most catastrophic instances, it could result in the failure of the entire piping system. One more consequence of excessive condensation taking place within your insulation involves the loss of that insulation's efficiency. If the wrong insulation material is chosen, it actually can absorb and retain any moisture from the condensation that's taking place. It's widely known in the industry that insulation becomes much less effective when it's allowed to become saturated with water. This can lead to thermal bridging, allowing more heat gain back into your chilled water supply lines, which will lead to energy losses and increased costs, requiring more energy to cool down those pipes back to that 40 or so degree operating temperature. This can also lead to a loss of process control. Warmer supply lines will lead to a diminished cooling effect in the commercial building as a whole. And this also puts extra strain on your equipment, putting added stress on the chillers in order to reduce the temperature of that water back down to the operating temperature that it needs to be at. Now that we've identified some of the most common issues associated with chilled water insulation failures, let's talk about some key considerations that can be made during the design phase of your system. Now, I'd like to start off just by covering some key terminology that we'll be using here today. Humidity is the concentration of water vapor present in any given airspace. Relative humidity is a percentage ratio that compares the actual amount of moisture in the air versus the amount it could theoretically hold at a given air temperature. Moving on, vapor pressure is the pressure at which water, both in liquid and vapor form, will exist in equilibrium for a given airspace temperature. Vapor pressure increases with air temperature, and because of this, warmer airspaces of high vapor pressure will move vapor towards colder areas of lower vapor pressure. And finally, the dew point is the temperature at which condensation will begin, and is a product of both temperature and relative humidity. When air cools to its dew point through contact with a surface that is colder than the air, water will condense onto that surface. One can view the topic of vapor pressure similar to that of normal pressure. That is, vapor will tend to move from areas of high pressure to low pressure. This phenomenon is commonly referred to as vapor drive. You can think of it as vapor moving from warm air to cold air, or in this case, towards the cold surface of a chilled water pipe. An insulation system with a compromised vapor barrier can allow this moisture in the air to move towards that cold pipe, where it can then condense into liquid moisture. This insulation system can become compromised due to initial poor installation or damage that happens after the fact, whether that be from maintenance activities or typical pedestrian traffic that happens to be in the area. When determining the right insulation material for your chilled water system, one property you may want to consider is the permeability of that insulation material. Permeability is the tendency of a material to allow liquids or gases to pass through it. Permeable insulations rely solely on the performance of an external vapor barrier to keep water vapor out of the system. If that vapor barrier becomes compromised, permeable insulations can allow water vapor to move towards the cold pipe, where it may then condense along the surface as dew. This condensed water can then be absorbed and retained into the insulation, which can compromise the K value, leading to a lower external surface temperature of the insulation. And you end up with a situation where you not only have condensation taking place on the chilled water pipe, but potentially on the external facing of the insulation itself. As you can see on the right, closed cell insulations typically tend to have a much lower vapor permeability than open cell and granular types of insulations. Now, I mentioned it briefly just there, but surface temperature of your insulation actually plays a pivotal role in proper condensation control. Proper insulation thickness is necessary to prevent surface condensation or sweating from occurring on the system. Our goal should always be to ensure that the insulation surface temperature is greater than the surrounding air's dew point. Below, you can see we have a chilled water pipe of 40 degrees Fahrenheit with an ambient air of 80 degrees and a relative humidity of 75%. This gives us a dew point of 71.3 degrees. In this example, we make sure to use enough insulation thickness to achieve a surface temperature of 74 degrees. Safely preventing surface condensation from occurring on our insulation. One thing I'd like to mention is that even in this scenario, there exists a point within the insulation thickness where the temperature falls to the dew point. However, as long as the system's vapor barrier remains intact, water vapor will not be able to penetrate to the point where it can freely condense. Within the industry, there exists many different standards from different organizations to help aid in the design of commercial insulation systems. One such standard is ASHRAE 90.1, the energy standard for buildings except low-rise residential buildings. This standard is commonly referenced in determining thickness requirements for chilled water lines. However, it should be noted that this standard is built around energy conservation, not around condensation control. In reality, necessary insulation thickness should be calculated for each set of parameters and ambient conditions that's unique to your system. Another piece to consider when designing your chilled water system is the geographic location of your project. Different parts of the country are subject to different temperatures and relative humidities, which results in different vapor pressures. Here we have a rough illustration of the annual mean maximum dew point temperature that various parts of the country typically experience. Condensation becomes a critical concern and a much more likely problem to encounter in high humidity environments where there exists a much higher vapor drive from ambient air towards a cold pipe surface. As a quick note, I'd like to point out that this map shows the average max dew point, but does not showcase extreme conditions that individual locations may experience. Of course, there exist multiple important but less obvious considerations that can often contribute to system failure. For indoor locations, you'll want to consider the environment and any additional risk factors that could contribute to increased humidity exposure. If the integrity of the building envelope is less than ideal, one may need to account for non-conditioned, high humidity air coming into contact with the chilled water systems. As an example, in an airport, this may occur at frequently opening doors, terminal gates, or conveyor openings within baggage claim areas. Another risk factor is whether or not a given building will be subject to what's referred to as idle building syndrome. If a commercial building is designed to be unoccupied at times, they may choose to shut down the air handlers of the HVAC system. However, the chillers and chilled water pipes are often required to remain operational. This combination of unconditioned ambient air, along with the same cold chilled pipe surface, can create a prime environment for condensation to take place. In any scenario, you'll want to consider your specific environment and always design around the worst case conditions expected for your system. Similar to indoor environments, outdoor chilled water systems may be subject to additional risk factors that need to be considered. It's imperative to ensure that any materials subject to direct sunlight have adequate UV resistance. Seasonal extremes in temperature and humidity will also need to be determined and taken into account. If in a location where exposure to chemical fumes is likely, chemical resistance to such materials may prove critical. Other important questions to ask may include, does your material withstand the burrowing activities of any local rodents or vermin? For direct buried systems, will materials withstand the compression load of soil backfill? If in high traffic areas, will materials withstand mechanical damage from pedestrian traffic or simply from the elements? Once again, the worst case conditions for your specific system should be determined and designed around. Yet another design consideration of your insulation system that should not be ignored involves the emissivity of the outermost jacketing to be used. Emissivity is the relative effectiveness of a surface to emit and absorb heat by radiation. It's expressed as a ratio between 0 and 1 and is most relevant to the outermost jacketing to be used on an insulation system. The higher the emissivity value, the more heat transfer will occur between the material and its environment via radiation. When considering chilled water pipes in warm environments, low emissivity jacketing materials, such as aluminum and steel, will absorb less heat from their surroundings via radiation, which will result in a lower jacketing surface temperature. Conversely, high emissivity jacketing materials, such as PVC and ASJ, will absorb more heat from their surroundings, yielding an overall higher surface temperature for the same system in that environment. Here we can look at exactly how this effect comes into play in our design considerations. In our example, we have two 8-inch chilled water pipes operating at 40 degrees Fahrenheit, each insulated with an unnamed Type X insulation. There's no wind and the ambient air is 90 degrees with 80% relative humidity, giving us a dew point of 83 degrees Fahrenheit. When covering our insulation with brand new aluminum jacketing, the surface temperature we get is 81.9 degrees. This is less than the dew point of the surrounding air and becomes an immediate concern for surface condensation on the jacketing to take place. However, when we take the same system and cover it with PVC jacketing, more heat from the environment is allowed to transfer onto the jacketing surface, giving us a surface temperature of 86.7 degrees, safely above the dew point where surface condensation would become an issue. As we've now discussed, there are multiple factors that go into designing a successful insulation system for a chilled water application. As a recap, when designing your system, you'll want to always determine the worst case conditions of your environment and plan accordingly. This includes the max temperature and relative humidity to be expected for the environment, as well as any indoor and outdoor complications that may be applicable. You'll want to be sure to calculate the thickness necessary to prevent surface condensation from taking place, taking into account the emissivity of the jacketing that will be used. And finally, be sure to allow adequate spacing between and around pipes for the insulation to be installed. When selecting an insulation material for a high-risk environment, consider a material that is closed cell and non-absorbent, with a low to zero water vapor permeability. It should be dur enough to tolerate its environment and have a compressive strength to withstand any weight that will come to rest against it, especially for direct burial and pipe support applications. And finally, proper installation and inspection should be carried out during construction to ensure the system is properly installed and sealed against moisture intrusion. Finally, I'd like to take some time to discuss some special considerations to take for chilled water pipes that exist in underground applications. An immediate challenge that direct buried systems present involves the forces of different loads that the piping and insulation will be subject to. Here we can see two different types of loads that should be considered and understood. Soil load refers to the direct weight exerted on a pipe from the above soil backfill. This will increase as soil density does, as well as with burial depth. Conversely, live load refers to the weight transferred to the pipe from heavy or moving objects from the above ground surface. This could be in the form of a stagnant load, such as a building, or dynamic load, such as vehicles on a roadway. This live load will increase as the weight and movement of the object increases. The load will also be larger for pipes with large outer diameters, as well as in areas of shallow burial depths. In any case, the combined load the piping and insulation system will be subject to should be considered, and an insulation material with sufficient compressive strength to withstand these loads should be specified accordingly. Hydrostatic pressure within ground soil should also be considered on direct buried systems. Hydrostatic pressure is the pressure exerted by a fluid at equilibrium at a given point within the fluid due to the force of gravity. This becomes a greater factor in high water table locations and areas that experience seasonally high levels of precipitation, and it generally will increase with soil depth. The pressure generated can drive water into insulation systems via gaps or breaches of the system's moisture barrier, particularly at joints and protrusions. In the case of absorbent insulations, it can then seep in and saturate the insulation material, compromising thermal performance. In these areas, a closed cell and non-absorbent insulation material should be considered in order to mitigate the risk of insulation failure due to moisture ingress. For underground systems that exist in tunnels and aren't direct buried, it's important to note that steam and chilled water lines may often share the same space within a tunnel. This will increase the vapor drive from warm air to the chilled water piping surface, increasing the emphasis placed on the vapor barrier and the permeability of the insulation material. It's also worth noting that tunnels many times are subject to flooding, which will put a greater emphasis on the water absorption properties of the insulation itself. Now that we've come this far, I'd like to take a moment to discuss one solution in particular that may be considered for your chilled water insulation systems, and that is FOAMGLAS Cellular Glass Insulation, a zero permeability approach. Starting off, for those that may not be familiar, FOAMGLAS Cellular Glass Insulation is a lightweight, rigid material composed of millions of completely sealed glass cells. It has a wide surface temperature range from -450 degrees Fahrenheit to positive 900 degrees, and its closed cell structure and inorganic nature lend to some unique properties amongst insulation materials within the industry. Foam glass is completely impermeable, with a water vapor permeability rating of 0. It does not require the use of an external vapor barrier to achieve this, as the insulation itself acts as its own vapor barrier. It also boasts a relatively high compressive strength when compared to other insulation materials in the industry, making it suitable for direct buried and pipe support applications. It's also relatively dimensionally stable, having a thermal expansion coefficient similar to that of carbon steel, which makes it suitable for wide temperature cycling applications as well. Being 100% inorganic and made of glass, foam glass is non-combustible and does not give off dangerous gases in the event of a fire, making it suitable for fire protection and fire stop applications. It's also resistant to the nesting activities of common vermin that may be found in an area, and is chemically resistant in a similar fashion to many typical glass beakers you might see in a laboratory. Finally, it's easy to cut and can be prefabricated to many different shapes and configurations prior to arriving on a job site. While foam glass itself is an impermeable material, it is important to ensure all joints and terminations between pieces of insulation are sealed in order to maintain an impermeable insulation system. For this reason, foam glass should be paired with a suitable joint sealant in order to maintain a continuous vapor barrier throughout the system. On chilled water indoor lines, this would be our Pit Seal CW sealant, which requires no primer and is VOC compliant to modern LEED building requirements. Finally, I'd like to wrap things up today by discussing some technical services that Owens Corning offers to those in the industry that we partner with. We maintain over 125 different commercial and industrial insulation system guide specifications. These can be used as a guide for engineers, specifiers, contractors, and facility owners to aid in the design, installation, and maintenance activities around their insulation systems. They include products, drawing details, and installation guidelines depending on the insulation application. And we're also very happy to help review client specifications and provide advice to our clients to improve their specifications when needed. Here's an example of one of our detailed drawings that we offer, specifically for our chilled water systems. We generate drawings like these regularly to help bridge the gap between specification and field installation, and to increase the confidence level that proper application techniques are being utilized on a job site. We maintain and utilize a full suite of proprietary thermal calculation softwares to help aid in the design for those who specify our insulation systems. If you have questions as to what insulation thickness or jacketing material to use in order to achieve a certain surface temperature, if you're curious about cost-saving potential, or have general questions about process control, we'd be happy to assist with a thermal calculation report tailored to your specific system. We also provide on-site support around process improvement and energy savings. We have multiple certified thermographers on staff, myself included, where we can arrive on-site to perform infrared inspection surveys and conduct heat flow measurement and analysis. We can then issue a current insulation condition report, evaluate energy losses and savings potential, and provide advice on insulation system improvements to consider. And finally, we are seen as the industry leader in education, training, and startup support. We hold frequent training sessions that allow us to build relationships with our customers through shared experiences. These allow engineers and specifiers to become more familiar with our systems and allow contractors to better understand how to effectively install them in order to achieve the best performing system possible. Here you can see one of our global training centers located in Houston, Texas, where we frequently host these training opportunities. Please reach out to us with any interest on how we can collaborate with you and your team. Once again, I'd like to thank everyone for joining us here today for this webinar. You can see my email address listed on the slide in front of you, as well as the email address and phone number for our FOAMGLAS technical services and training team. We'd be happy to work with you after the fact and any questions you may have. With that, I'd like to pass the mic over to Kelly as we open up the Q&A portion of the presentation. Kelly?
Wow, what a great presentation, Alec. Thank you so much for all that valuable information. Hello, everyone. My name is Kelly Santiago, and I'm on the Technical Insulation Marketing team here at Owens Corning, and I'm excited to spend this time with you learning more about insulating chilled water systems. So at this time, I'd like to get into some of the questions that came in during this webinar. And Alec, if you're ready, let's get to the first one.
Absolutely.
All right. What are important locations to apply vapor stops on an insulation system?
Yes, this is a good question. So we mentioned earlier that protrusions and terminations are very common fail points for below ambient systems. That's often where you have the sharpest changes in geometry. It's where you're having to cut insulation pieces to match some of the fittings to on these closed systems, and that can often be an entry point if it's not installed correctly. So taking proper care to make sure that you have a fully closed system using an appropriate sealant or other accessory at joints and protrusions can be important. Also, we recommend if there's any anticipated stop in work for the day on a project, if you're taking a break or if you're wrapping things up to come back the next day, we recommend using joint sealant to make temporary vapor stops at the end of a last section of insulation that you may have put on a piece of piping. So just because you haven't reached the termination for that stretch of piping, if you're stepping away from the job site for any reason whatsoever, make a temporary vapor stop using joint sealant at that location, and then pick back up with your insulation being put on the pipe whenever you come back. So temporary vapor stops whenever stepping away from a job site is always a good rule of thumb.
Great, that makes a lot of sense. Okay, a second question for you, Alec. How can I determine what surface temperature my insulation jacketing will be?
So we actually help with inquiries like this all the time. There are a lot of parameters to take into account, including operating temperature of your pipe, the type of insulation you're considering using, the thickness of insulation that you're considering putting on, and the emissivity jacketing, as we mentioned all before. We're happy to help with this exact scenario, and we can take a look at your exact parameters, and we have a whole suite of proprietary thermal calculation softwares that we can assist and show you, hey, this is your pipe, these are your conditions, and here's the thickness and type of insulation you should be looking at to achieve that condensation from taking place. So long story short, there's a lot of math that goes into it. We'd be happy to help with that math for you and your system.
Great. Okay, this looks like this might be our final question then. Do you offer the possibility of virtual trainings?
Yes, absolutely. We pride ourselves on being very flexible with how we train those who we partner with. We highlighted our training center in one of those last slides, and we showed a picture of our nice facility in the Houston area. However, we understand oftentimes it can be a hassle to get a large number of employees out to our site on certain occasions. So if you have a certain job or project that you need help with, we frequently will host virtual trainings where we put on presentations just like this so that employees can get a comfortable level of knowledge of the product beforehand. We also have the possibility of doing traveling trainings to either a project location or a client's facility themselves. It's all on a one-on-one basis. We'd be happy to work with you, see what type of trainings you and your team would benefit from. But with that, yes, we're very flexible, and we'd be happy to work with you on the trainings that you need.
Okay. Okay, looks like we got another question that came in. Is there any other type of insulation that can be used for direct bury, or is FOAMGLAS the only one?
A good question for sure. I can't stand up here and say that FOAMGLAS is the end-all only solution for any type of application. There's a lot of nuance to the insulation business, and there's a lot of different materials out there with
that all bring unique properties to the table. I will say foam glass is widely used for direct buried applications because of its combination of impermeability and high compressive strength, two very key components to a lot of underground buried systems. It's not the only high compressive strength insulation. There are other insulations that will be able to tolerate the loads that soil backfill and live load will bring to the table. But especially for below ambient applications where you're not only concerned about water from the ground getting in, but also from high vapor drive should that pipe come up from underground and be in a chiller room at some point. That pipe's going to lead to something. Foam glass just brings a unique blend of impermeability, not absorbency, and high compressive strength to the table. So it's not the only underground insulation, but it is widely used for that unique blend of properties.
Great. Okay, well, it looks like that may have been our last question. So thank you to everybody who sent one in to the chat. Thank you for spending time with us today. We hope you found this information important and beneficial, and we look forward to having some more webinars like this in the future. So be on the lookout. Thanks again.
Thank you, everyone.